Maxwell's equations are a set of partial differential equations that, together with the Lorentz force law, form the foundation of classical electrodynamics, classical optics, and electric circuits. These fields in turn underlie modern electrical and communications technologies. Maxwell's equations describe how electric and magnetic fields are generated and altered by each other and by charges and currents. They are named after the physicist and mathematician James Clerk Maxwell, who published an early form of those equations between 1861 and 1862. The equations have two major variants. The microscopic set of Maxwell's equations uses total charge and total current, including the complicated charges and currents in materials at the atomic scale. It has universal applicability but may be infeasible to calculate. The macroscopic set of Maxwell's equations defines two new auxiliary fields that describe large-scale behavior without having to consider these atomic scale details. But it requires the use of parameters characterizing the electromagnetic properties of the relevant materials. The term Maxwell's equations is often used for other forms of Maxwell's equations. For example, space-time formulations are commonly used in high-energy and gravitational physics. These formulations, defined on space-time rather than space and time separately, are manifestly compatible with special and general relativity. In quantum mechanics and analytical mechanics, versions of Maxwell's equations based on the electric and magnetic potentials are preferred. Since the mid-20th century, it has been understood that Maxwell's equations are not exact but are a classical field theory approximation to the more accurate and fundamental theory of quantum electrodynamics. In many situations, though, deviations from Maxwell's equations are immeasurably small. Exceptions include non-classical light, photon scattering, quantum optics, and many other phenomena related to photons or virtual photons. Formulation in terms of electric and magnetic fields. The powerful and most widely familiar form of Maxwell's equations, whose formulation is due to Oliver Heaviside, in the vector calculus formalism, is used throughout unless otherwise explicitly stated. Symbols in bold represent vector quantities, and symbols in italics represent scalar quantities, unless otherwise indicated. The equations introduce the electric field, E, a vector field, and the magnetic field, B, a pseudovector field, where each generally have time dependence. The sources of these fields are electric charges and electric currents, which can be expressed as local densities, namely charge density ρ and current density J. A separate law of nature, the Lorentz force law, describes how the electric and magnetic field act on charged particles and currents. A version of this law was included in the original equations by Maxwell but, by convention, is no longer. In the electric and magnetic field formulation there are four equations. Two of them describe how the fields vary in space due to sources, if any, electric fields emanating from electric charges in Gauss's law, and magnetic fields as closed field lines not due to magnetic monopoles in Gauss's law for magnetism. The other two describe how the fields circulate around their respective sources. The magnetic field circulates around electric currents and time varying electric fields in Amperes Law with Maxwell's addition, while the electric field circulates around time-varying magnetic fields in Faraday's law. The precise formulation of Maxwell's equations depends on the precise definition of the quantities involved. Conventions differ with the unit systems, because various definitions and dimensions are changed by absorbing dimensionful factors like the speed of light c. This makes constants come out differently. Conventional formulation in SI units. The equations in this section are given in the convention used with SI units. Other units commonly used are Gaussian units based on the CGS system, Lorentz Heaviside units, and Planck units. See below for the formulation with Gaussian units. where the universal constants appearing in the equations are the permittivity of free space, epsilon 0, and the permeability of free space, mu 0. In the differential equations, a local description of the fields, the nabla symbol, denotes the three-dimensional gradient operator, and from it, the divergence operator is. The curl operator is times. The sources are taken to be the electric charge density, ρ, and the electric current density, J. In the integral equations, a description of the fields within a region of space, omega is any fixed volume with boundary surface omega, and sigma is any fixed open surface with boundary curve sigma, is a surface integral over the surface omega, is a volume integral over the volume omega, is a surface integral over the surface sigma, is a line integral around the curve sigma. Here fixed means the volume or surface do not change in time. Although it is possible to formulate Maxwell's equations with time-dependent surfaces and volumes, this is not actually necessary. The equations are correct and complete with time-independent surfaces. The sources are correspondingly the total amounts of charge and current within these volumes and surfaces, found by integration. The volume integral of the total charge density, ρ, over any fixed volume, omega, is the total electric charge contained in omega, where dV is the differential volume element, and the net electric current is the surface integral of the electric current density, J, passing through any open fixed surface, sigma, where ds denotes the differential vector element of surface area, S, normal to surface. The total charge or current refers to including free and bound charges, or free and bound currents. These are used in the macroscopic formulation. Relationship between differential and integral formulations. The differential and integral formulations of the equations are mathematically equivalent by the divergence theorem in the case of Gauss's law and Gauss's law for magnetism, and by the Kelvin-Stokes theorem in the case of Faraday's law and Amperes law. Both the differential and integral formulations are useful. The integral formulation can often be used to simplify and directly calculate fields from symmetric distributions of charges and currents. On the other hand, the differential formulation is a more natural starting point for calculating the fields in more complicated situations. For example, using finite element analysis, flux and divergence, the fields emanating from the sources can be inferred from the surface integrals of the fields through the closed surface omega, defined as the electric flux and magnetic flux, as well as their respective divergences E and B. These surface integrals and divergences are connected by the divergence theorem. Circulation and curl. The circulation of the fields can be interpreted from the line integrals of the fields around the closed curve sigma, where d is the differential vector element of path length tangential to the path curve, as well as their curls. These line integrals and curls are connected by Stokes' theorem, and are analogous to quantities in classical fluid dynamics. The circulation of a fluid is the line integral of the fluid's flow velocity field around a closed loop, and the vorticity of the fluid is the curl of the velocity field. Time evolution. The dynamics, or time evolution of the fields, is due to the partial derivatives of the fields with respect to time. These derivatives are crucial for the prediction of field propagation in the form of electromagnetic waves. Since the surface is taken to be time-independent, we can make the following transition in Faraday's law. See differentiation under the integral sign for more on this result. Conceptual descriptions. Gauss's law. Gauss's law describes the relationship between a static electric field and the electric charges that cause it. The static electric field points away from positive charges and towards negative charges. In the field line description, electric field lines begin only at positive electric charges and end only at negative electric charges. Counting the number of field lines passing through a closed surface, therefore, yields the total charge enclosed by that surface divided by dielectricity of free space. More technically, it relates the electric flux through any hypothetical closed Gaussian surface to the enclosed electric charge. Gauss's law for magnetism. Gauss's law for magnetism states that there are no magnetic charges, analogous to electric charges. Instead, the magnetic field due to materials is generated by a configuration called a dipole. Magnetic dipoles are best represented as loops of current but resemble positive and negative magnetic charges, inseparably bound together, having no net magnetic charge. In terms of field lines, this equation states that magnetic field lines neither begin nor end but make loops or extend to infinity and back. In other words, any magnetic field line that enters a given volume must sum or exit that volume. Equivalent technical statements are that the sum total magnetic flux through any Gaussian surface is zero, or that the magnetic field is a solenoidal vector field. Faraday's law. The Maxwell-Faraday's equation version of Faraday's law describes how a time-varying magnetic field creates an electric field. This dynamically induced electric field has closed field lines just as the magnetic field, if not superposed by a static electric field. This aspect of electromagnetic induction is the operating principle behind many electric generators. For example, a rotating bar magnet creates a changing magnetic field, which in turn generates an electric field in a nearby wire. Amperes Law with Maxwell's addition. Amperes Law with Maxwell's addition states that magnetic fields can be generated in two ways, by electric current and by changing electric fields. Maxwell's addition to Amperes Law is particularly important. It shows that not only does a changing magnetic field induce an electric field, but also a changing electric field induces a magnetic field. Therefore, these equations allow self-sustaining electromagnetic waves to travel through empty space. The speed calculated for electromagnetic waves, which could be predicted from experiments on charges and currents, exactly matches the speed of light. Indeed, light is one form of electromagnetic radiation. Maxwell understood the connection between electromagnetic waves and light in 1861, thereby unifying the theories of electromagnetism and optics. Vacuum equations, electromagnetic waves and speed of light. In a region with no charges and no currents, such as in a vacuum, Maxwell's equations reduce to taking the curl of the curl equations, and using the curl of the curl identity times equals minus 2x, we obtain the wave equations, which identify with the speed of light in free space. In materials with relative permittivity, epsilon r, and relative permeability, mu r, the phase velocity of light becomes which is usually less than c. In addition, E and B are mutually perpendicular to each other in the direction of wave propagation, and are in phase with each other. A sinusoidal plane wave is one special solution of these equations. Maxwell's equations explain how these waves can physically propagate through space. The changing magnetic field creates a changing electric field through Faraday's law. In turn, that electric field creates a changing magnetic field through Maxwell's addition to Amperes' law. This perpetual cycle allows these waves, now known as electromagnetic radiation, to move through space at velocity microscopic versus macroscopic. The microscopic variant of Maxwell's equation is the version given above. It expresses the electric E field and the magnetic B field in terms of the total charge and total current present, including the charges and currents at the atomic level. The microscopic form is sometimes called the general form of Maxwell's equations. The macroscopic variant of Maxwell's equation is equally general, however, with the difference being one of bookkeeping. The microscopic variant is sometimes called Maxwell's equations in a vacuum. This refers to the fact that the material medium is not built into the structure of the equation. It does not mean that space is empty of charge or current. Maxwell's macroscopic equations, also known as Maxwell's equations in matter, are more similar to those that Maxwell introduced himself. Unlike the microscopic equations, the macroscopic equations separate out the bound charge QB and bound current IB to obtain equations that depend only on the free charges QF and current CF. This factorization can be made by splitting the total electric charge and current as follows. Correspondingly, the total current density J splits into free JF and bound JB components. And similarly, the total charge density ρ splits into free ρf and bound ρb parts. The cost of this factorization is that additional fields, the displacement field D and the magnetizing field H, are defined and need to be determined. Phenomenological, constituent equations relate the additional fields to the electric field E and the magnetic B field, often through a simple linear relation. For a detailed description of the differences between the microscopic and macroscopic variants of Maxwell's equations, see below. Bound charge and current. When an electric field is applied to a dielectric material, its molecules respond by forming microscopic electric dipoles. Their atomic nuclei move a tiny distance in the direction of the field, while their electrons move a tiny distance in the opposite direction. This produces a macroscopic bound charge in the material even though all of the charges involved are bound to individual molecules. For example, if every molecule responds the same, similar to that shown in the figure, these tiny movements of charge combine to produce a layer of positive bound charge on one side of the material and a layer of negative charge on the other side. The bound charge is most conveniently described in terms of the polarization P of the material, its dipole moment per unit volume. If P is uniform, a macroscopic separation of charge is produced only at the surfaces where P enters and leaves the material. For non-uniform P, a charge is also produced in the bulk. Somewhat similarly, in all materials the constituent atoms exhibit magnetic moments that are intrinsically linked to the angular momentum of the components of the atoms, most notably their electrons. The connection to angular momentum suggests the picture of an assembly of microscopic current loops outside the material. An assembly of such microscopic current loops is not different from a macroscopic current circulating around the material's surface, despite the fact that no individual charge is traveling a large distance. These bound currents can be described using the magnetization M. The very complicated and granular bound charges and bound currents, therefore, can be represented on the macroscopic scale in terms of P and M, which average these charges and currents on a sufficiently large scale so as not to see the granularity of individual atoms, but also sufficiently small that they vary with location in the material. As such, Maxwell's macroscopic equations ignore many details on a fine scale that can be unimportant to understanding matters on a gross scale by calculating fields that are averaged over some suitable volume. Auxiliary fields, polarization and magnetization. The definitions of the auxiliary fields are, where P is the polarization field and M is the magnetization field, which are defined in terms of microscopic bound charges and bound currents, respectively. The macroscopic bound charge density ρb and bound current density Jb in terms of polarization P and magnetization M are then defined as if we define the total bound and free charge and current density by and use the defining relations above to eliminate D and H. The macroscopic Maxwell's equations reproduce the microscopic equations. Constitutive relations. In order to apply Maxwell's macroscopic equations, it is necessary to specify the relations between displacement field D and the electric field E, as well as the magnetizing field H and the magnetic field B. Equivalently, we have to specify the dependence of the polarization P and the magnetization M on the applied electric and magnetic field. The equations specifying this response are called constitutive relations. For real-world materials, the constitutive relations are rarely simple, except approximately, and usually determined by experiment. See the main article on constitutive relations for a fuller description. For materials without polarization and magnetization, the constitutive relations are where epsilon 0 is the permittivity of free space and mu0 the permeability of free space. Since there is no bound charge, the total and the free charge and current are equal. More generally, for linear materials the constitutive relations are where epsilon is the permittivity and mu the permeability of the material. Even the linear case can have various complications, however. For homogeneous materials, epsilon and mu are constant throughout the material, while for inhomogeneous materials they depend on location within the material. For isotropic materials, epsilon and mu are scalars, while for anisotropic materials they are tensors. Materials are generally dispersive, so epsilon and mu depend on the frequency of any incident M waves. Even more generally, in the case of nonlinear materials, D and P are not necessarily proportional to E. Similarly, B is not necessarily proportional to H or M. In general, D and H depend on both E and B, on location and time, and possibly other physical quantities. In applications, one also has to describe how the free currents and charge density behave in terms of E and B, possibly coupled to other physical quantities like pressure, and the mass, number density, and velocity of charge-carrying particles. E.g., the original equations given by Maxwell included Ohm's law in the form equations in Gaussian units. Gaussian units are a popular system of units, that is part of the centimeter-gram-second system of units. When using CGS units, it is conventional to use a slightly different definition of electric field. ECGs equals C-1 ESI. This implies that the modified electric and magnetic field have the same units. Then it uses a unit of charge defined in such a way that the permittivity of the vacuum epsilon 0 equals 1/4 pi c, hence mu 0 equals 4 pi c. Using these different conventions, the Maxwell equations become. Maxwell's equations are a set of partial differential equations that, together with the Lorentz force law, form the foundation of classical electrodynamics, classical optics, and electric circuits. These fields in turn underlie modern electrical and communications technologies. Maxwell's equations describe how electric and magnetic fields are generated and altered by each other and by charges and currents. They are named after the physicist and mathematician James Clerk Maxwell, who published an early form of those equations between 1861 and Kinetic properties of the relevant materials. The term Maxwell's equations is often used for other forms of Maxwell's equations. For example, space-time formulations are commonly used in high-energy and gravitational physics. These formulations, defined on space-time rather than space and time separately, are manifestly compatible with special and general relativity. In quantum mechanics and analytical mechanics, versions of Maxwell's equations based on the electric and magnetic potentials are preferred. Since the mid-20th century, in 1862, the equations have two major variants. The microscopic set of Maxwell's equations uses total charge and total current, including the complicated charges and currents in materials at the atomic scale. It has universal applicability but may be infeasible to calculate. The macroscopic set of Maxwell's equations defines two new auxiliary fields that describe large-scale behavior without having to consider these atomic scale details. But it requires the use of parameters characterizing the electromagnetism. It has been understood that Maxwell's equations are not exact but are a classical field theory approximation to the more accurate and fundamental theory of quantum electrodynamics. In many situations, though, deviations from Maxwell's equations are immeasurably small. Exceptions include non-classical light, photon scattering, quantum optics, and many other phenomena related to photons or virtual photons. Formulation in terms of electric and magnetic fields. the powerful and most widely familiar form of Maxwell's equations, whose formulation is due to Oliver Heaviside, in the vector calculus formalism, is used throughout unless otherwise explicitly stated. Symbols in bold represent vector quantities, and symbols in italics represent scalar quantities, unless otherwise indicated. The equations introduce the electric field, E, a vector field, and the magnetic field, B, a pseudovector field, where each generally have time dependence. The sources of these fields are electric charges and electric currents.